Hello and welcome to EP2P04. This is going to be Topic 2 in 2020, Damped Harmonic Motion and Resonance. So damped harmonic motion is when the amplitude of a periodic motion of an oscillator, so something that would have periodic motion, for example, a mass on a spring, decreases because of some kind of damping force that opposes the velocity. So damping force, unlike the spring force, which opposes kind of changes in position, the damping force opposes motion directly. It opposes velocity. So if you are displaced from equilibrium, a spring will try and restore you back to equilibrium with a force. If you are moving, if you have some velocity that's non-zero, kind of displaced from equilibrium velocity maybe, then a damping force will try to restore you to equilibrium velocity, similar to a spring, but for velocity. Okay, so when disturbed, i.e. moved away from equilibrium or given a velocity, an oscillator like this will respond harmonically at its natural frequency, unless the damping's too high, then it's at a slightly different frequency, dissipating energy away due to the damping and eventually returning to rest at its equilibrium position. So here's a cool link to Math Warehouse that you can use to explore this a little bit. What's going on is we have a mass on a spring. Math Warehouse is bringing us this. And this is showing what the response would be over time. You might remember from first year that a system like this oscillates with simple harmonic motion, and it is just a sinusoid forever. It will never change from that. The amplitude is just a constant. It is tossing energy between the maximum potential energy, where it's all potential at the maximum displacement, half k maximum displacement squared for the spring energy, and then at the center, half mv squared, when it's all kinetic energy, not potential. Maximum potential here, maximum kinetic there. Okay, now what we're doing differently here is adding in damping. So let's imagine that we've got some sort of resistive force that resists the motion. You can see it starts off with this same kind of sinusoidal motion, but the amplitude is lower. Every time it crosses, it doesn't go quite as far because a lot of energy is lost to a non-conservative friction-style damping force as it goes past as it's moving at any point, but most of the energy is lost when it has the maximum velocity. That's when the friction force is doing the most negative work here. The damping force is doing the most negative work on this. Okay, so it loses this energy that it had when you have damping and ends up with an amplitude that decreases over time, possibly going away entirely. You can see how the damping force is acting the most when the amplitude is the largest. So we've got like a quick reduction, and then because the velocity is never so large as it was again, the damping takes a lot longer to reduce the amplitude more and more. Okay, so that's a basic idea of what we'd expect in this system with a lot of damping in there. So that's the first part. We're going to be concerned with understanding how damping affects the motion of an oscillator system like this. The next thing is, once we have these damped oscillator systems, we're going to be looking at how to drive them with an external force and how they respond at different frequencies. At certain frequencies, they're going to be responding a lot with a lot more amplitude than the force that we're driving them with would have produced if it was not at resonance. This is a YouTube video that shows this off, and let's see if we can get this to work. So this is by Science for All. Make sure to like and subscribe and all that. Okay, so anyway, what we have here is we've got an oscillating platform, and this is going back and forth at a frequency that's going to increase. So it starts off very slow, and then eventually it's going to be going very fast back and forth. Now, when we're at a really low frequency, not much is happening. You see all the masses on top of these springs, kind of spring-like things by having these long extended arms, are going to be oscillating back and forth with the platform. But then the one with the longest arms, and therefore the lowest spring constant, and then the lowest root k over m, lowest frequency, is going to be driven into resonance first. So what we'll see as you start to increase this, there we go, at a certain frequency, it has a really high amplitude. It goes back and forth quite a lot compared to what the platform is doing. It's moving more than the platform. Then at a higher frequency, we have the same effect happen for the middle one, and at an even higher frequency, the shortest spring ends up oscillating with a large amplitude. So this is the resonance effect that we're looking for. There's all kinds of other details around this. So if you look really closely, you'll see some cool stuff happening with the phase too. So at low frequency, everything is moving just back and forth with the platform as expected. When you go to the resonant frequency, this moves a little bit after the platform. Can you see that? Right, so this is actually 90 degrees out of phase with the platform. It's a quarter cycle behind what's going on. And this kind of emphasizes why the resonance effect is working. When somebody's on a swing, right, they're going back and forth on a swing, you push them when their velocity is a maximum, and that's what's going to be adding to their motion. That's going to add in energy with every cycle, and that's what's going on with a resonance effect like this. So by ending up 90 degrees behind in position, what this driving force is doing, this ends up moving and pushing on this at just the right time to be adding energy every cycle so that it's going to reach an equilibrium when the damping cancels out this when it's at a much higher amplitude than this is at. Okay, so that's some neat stuff that goes on with phase. When you're at resonance, it ends up 90 degrees behind phase, and when you're above resonance, it's 180 degrees out of phase, and the amplitude is really a lot smaller. So this is still responding with the same frequency as this, just 180 degrees out of phase, and cut down in amplitude a lot because of that. So that's the effect. That's the set of effects that we expect to see with damping and with resonance. And all the setup that we need to model this is analyzing a mass on a spring with a damper and then applying forces to this at various frequencies. So that's going to be the subject of what we're doing this week, examining how these sorts of systems respond, how to get those cool effects that we're seeing and understand them, and derive all of this mathematically. While we're talking about masses on springs, this is useful for all kinds of different systems. So this is going to be applicable to RLC circuits, to like magnetic pendulums over aluminum plates, musical instruments, earthquake protection for buildings, audio amplifiers and filters, and piezoelectric quartz tuning forks for keeping time in electronic systems, to name a few. Or, if you like lasers, then this is also a lot to do with how lasers and optical systems work, making the internet faster. So that's kind of cool too. All right, let's get to it. Suppose we have a mass attached to a spring and a damper, and the spring puts out a force, negative k times x, where x is the displacement from equilibrium. Notice that this is always in a direction that opposes what x is. If x is positive, it puts a negative force. If x is negative, it puts a positive force. So this restores the mass to the equilibrium position that the spring wants it to have. The damper works the same way, but for velocity. If velocity is positive, this puts a force in the negative direction. If we're moving to the right, this tries to slow it down. It says, hey, wait up. And if we're moving to the left, this says, whoa, 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 and pushes off on it to slow this thing down again. Okay, so this is the force. And by Newton's second law, this is equal to mass times acceleration. Rearranging and writing everything in terms of derivatives of x, we have this, ta-da, which is a linear, homogeneous, second-order differential equation. So what we're going to be doing is going over how the solution to this differential equation works analytically. This is using material from Math 2 Z03. I'll take some time and actually derive this, which might help you out with that math course, or could be a review if you've already done that. And this is some interesting stuff, because now we have a set of useful analytic solutions to this differential equation, one of which involves decaying exponential functions, another one involves decaying exponential with a linear term, and a third of which involves decaying exponential envelope, this same kind of thing, e to the negative b over 2m times t, multiplied by these oscillatory terms. This is the kind of one that we were looking at in this form up here. So this is this sinusoidal oscillatory term, right? That's not going to happen in these first two kinds of solutions that we have here, where we have just decaying exponential terms. Those don't bounce back and forth across the axis. So that thing that we're showing is this third case, which is called the underdamped case. Okay, so those are the things that we're going to look at. This differential equation analytically leads to three forms of solution that depend on how large the b term is. So let's explain what we mean by linear differential equation. When you call something a linear differential equation or a linear function, what you're saying is that it has the properties that a line through the origin has. So a line through the origin is y equals m times x. And this has the interesting and useful mathematical property that if you know what y at, let's say this is our y at x, right? So this as a function, y at x, has the property that y at a times x1 plus b times x2 happens to be a times y at x1 plus b times y at x2. So multiplying a point by a, taking a sort of further, and then adding that to another point that is also scaled is the same as if you were to first evaluate the function on each of those points and then scale it accordingly. So this is just this is not so hard to prove for a simple function like this that's just multiplied. You can try it out yourself. Let's see. Y at this thing would be equal to m times ax1 plus bx2, which is equal to, after distributing the m through this, we're going to have a, so let's say m, let's do it in a bunch of steps. ma, oh, that's a function. Better not do it that way anyway. Okay, so a times m x1 plus b times m x2, and well, we're done. This is proven that this function is a linear function. Linear function meaning that y at a linear combination of some set of arguments for this thing is equal to a linear combination of the function evaluated at those arguments. So that's what's true of a linear function. Rather than, if you know what y at x1 is, and you know what y at x2 is, and you know that y is linear, then you can find y at ax1 plus bx2 by just taking a y at x1 plus b y at x2. So you can distribute the function over a sum, and you can pull constant multiples out of the function. Now, because time derivatives are linear operators themselves, this combination here, this thing, mx double dot plus bx dot plus kx, this is a linear operator, right? This thing on the left. You might think that maybe you could specify the linear operator of this differential equation, like the left-hand side, as, let's say, a linear operator on some function of t would be equal to, or defined as, m times the second derivative times f at t plus b times the first derivative of f at t plus k times f at t. Now, if we define this operator to be the operator of doing this differential equation term on the left, it's not really the full equation, it's just the left-hand side of this differential equation, then this operator itself is linear because these derivative operators and multiplying by constants are linear. We can demonstrate that. So here's L at f at t, right? L at, let's say, g at t would then be equal to m g double prime plus b g prime plus g. And we could show that it's linear by seeing what L times maybe a f at t plus b g at t would be equal to. So let's pretend we don't know that it's linear already, and we'll substitute in this for the thing that's after the derivatives there. So when we sub it in, we're going to have this term in place of all of the f at t's there. Okay, so then the derivatives and the mass multiplication can be distributed through this, and the a's and b's pulled out, because derivative of a sum is the sum of the derivatives, and you can pull constants out of derivatives. So this means we're going to have a times m f double prime plus m. Okay, let's not jump too far ahead. So a m f double prime plus b times m g double prime plus b times a f prime plus b times b g prime plus k times a f prime, no prime, k times a f plus k times b, and it's cut off at the end, g. Okay, now let's factor out all the big A's and big B's. So we've got big A times mf double prime plus bf prime plus kf, and the b term similarly will get mg double prime plus, inside the brackets, plus bg prime plus k times g. So this is a times this L operator at f at t plus b times the L operator at g at t. Aha! So this means this differential equation is indeed a linear function. So the operator on the left-hand side taking this set of derivatives, as we've got for our differential equation that we've set as a linear differential equation, is behaves this linearity property, that you could know what the result of substituting in a times one function plus b times another function is for this differential equation, if you know what the result is of substituting in each of those functions themselves by just taking this sort of thing, this linear combination of it. So why is that useful? Well, it means that if we find two solutions, let's say x1 and x2, then we know that any linear combination of them is also a solution, because for it to be a solution means you substitute it in and you get 0. And if you sub in one function over here and you get 0, and you sub in another function and you get 0, then if you sub in, because it's linear, a constant times one and a constant times another, then you're still going to get 0. Let me show you what I mean by that. Suppose we've got two functions. x1 is a solution, meaning that L at x1 is equal to 0, and x2 is a solution, L at x2 is equal to 0. Then, because this is a linear operator on the left, L at a x1 plus b x2 must be equal to a L at x1 plus b L at x2, which is a times 0 because x1 was a solution, plus b times also 0 because x2 was a solution, and that's just 0. Okay, so that's what's really useful about solving linear differential equations if they're homogeneous, that once you found one solution and another solution, any linear combination of them is necessarily also a solution. So that's some of the tricks about how linear differential equations work in general. This linearity property turns out to be very useful for forming combined solutions once you have a solution. But how do you get that first solution? Well, that depends on what the coefficients are of the dependent variable term, so the x's and its derivatives here. In this case, we have constant coefficients, so you can find a solution by assuming that x is e to the rt and then seeing if you can get that to work. It turns out you can, as long as r is certain specific values. So by substituting this in, you can check this for yourself. You can then factor out the e to the rt from what you get when you substitute this form into here and find that, okay, this works as long as this thing, or e to the rt, is 0. But e to the rt is never 0, so it must mean that this thing in front is 0, which means r has to be negative b plus or minus root b squared minus 4mk over 2m. That's just the quadratic formula. So what does this mean for the solutions? Well, it depends on how big b is, physically how big the damping is compared to other things. If the damping is so big that b squared is greater than 4mk, then we end up with two real roots for this. So two real roots here, and that means two values of r, which both end up being negative, because b squared minus 4mk, m and k are both positive in this case, because m is the mass and k is the spring constant, so b squared minus 4mk is less than b squared. So the root of this is less than b. So even when you take the positive root, it doesn't make something that's positive again. B is negative as well. So then we've got two negative roots if b squared is greater than 4mk, and that means the solutions we found are both e to the something negative times time, so decaying exponentials. If you take a linear combination of those, you'll find the general solution, but it's just the sum of two decaying exponentials, which means that if damping is big, then the mass is going to return to equilibrium by a decaying exponential function. Okay. If the b squared is exactly 4mk, you have a special case where you get only one root, which is 0. Then this is negative b over 2m, and we can find another solution through the math technique reduction of order, which ends up being the same thing, e to the negative b over 2mt times t. And this also looks like a decaying exponential function. Despite the plus t times this, it doesn't make much difference to how the graph looks. So this still decays back to the equilibrium position. But something special happens. If b squared is less than 4mk, then this root here ends up being the root of a negative number, so it's imaginary, and we can be a little bit more, we can write it a little bit more conveniently by factoring out an I from there. So factor out a negative under the root sign. The way that that works is as follows, just in case anybody's kind of wondering where that comes from. With b squared less than 4mk, then this thing is actually negative, but it's written in a way that doesn't show that. It's kind of a bit misleading. So if we factor out a negative 1, 4mk minus b squared is what we'll have left inside, and this is a better way to write it if b squared is less than 4mk, because then you've got a positive term here. And you can explicitly, kind of maybe clearly, factor out the negative there. So the root of negative 1 ends up just being I, the imaginary number there. And then this is a positive thing under the root right now. So we have negative b plus or minus this complex conjugate pair of roots, 4mk minus b squared under the root. Okay, so this thing leads itself to two solutions, which are these complex conjugate pair of roots in the exponent, but you can also rewrite these more conveniently using Euler's identity, because yeah, I have it written here for you. E to the I theta is cos theta plus I sine theta. It turns out that if you take these linear combinations, so the positive root 1 that we found, plus the negative root 1 divided by 2, you can work out that it's e to the negative b over 2m times cos of omega times t. What's omega? Omega is defined as a convenient thing as this, this root that we have, this root 4mk minus b squared over 2m, which you could take the 2m under the root and then make it a k over m minus a b squared over 4m squared. This is a term which is the damped frequency, or the damped resonant frequency, and we'll see why that is called that when we look at driving these mass spring systems. But in the meantime, this is just a substitution of convenience. Let's call this thing omega d, and then we can write, instead of cos of omega d, or rather instead of cos of this root times t, cos of omega d times t. And same thing, you can get a sine by taking this linear combination. So 1 over 2i times the positive root minus 1 over 2i times the negative root. So let's recap. When we have a system like this, mass attached to a spring and a damper, it leads to this differential equation, mx double dot plus bx dot plus kx is equal to 0. This is a linear second order homogeneous differential equation with constant coefficients, which means we can find solutions by assuming that x is e to the rt is a solution. When you substitute that into the differential equation, then you find out it works as long as r is negative b plus or minus root b squared minus 4mk over 2m. And this has three distinct forms depending on how big b is compared to 4mk. If b squared is bigger than that, then you have just two decaying exponential terms. If b squared is exactly the same size, you end up with almost the same thing, but with this 1t times that. And if b squared is smaller than that, you end up with cos and sine terms, which have the frequency of omega d given by root of k over m minus b squared over 4m squared. We can continue to explore these analytically by the next example, where you examine the difference that damping makes by finding the response of an overdamped, critically damped, and underdamped mass spring damper system when you pull the mass a distance x0 from its equilibrium position and then release it. So this means that the initial position is x0 and the initial velocity is 0. So released means no initial velocity. Okay, so we have the solutions already for overdamped, critically damped, and underdamped. Overdamped, it was this solution. So if we assume that x dot at 0 is 0 and substitute that in, then we can solve for what C1 and C2 are. So this is like an analytical form solution of it. If you go and substitute them back in, then it's nasty, but you've got this closed form solution. This is optional. You could imagine rewriting it as this, instead of these decaying exponentials, because there's a difference between them. You might think, what's the actual form of this look like? Maybe it's more convenient because they happen to be this specific pair of things. After you factor out the negative b over 2m exponent, then you're left with exactly the right form that you could creatively rewrite as a sinh and cosh function if you're interested in it. Anyway, it's a little bit hard to notice from this general form, but because root b squared minus 4mk is less than b, the decaying exponential term always dominates the rising exponential term of these. This is the same thing we noticed earlier when we said that the exponent was always negative for these, for the positive and negative roots, r's, that we found. Both of them are negative, even though it's called the positive root. It's the positive of this root, and the overall r is still negative. So that's why this is still a decaying exponential form. Okay, so that's the overdamped one. The critically damped works the same. You substitute in that x at 0 is x0, and that lets you solve for C1 right away. And then once we've got that, we can sub in x dot at 0 is 0 and solve for C2. This one's a lot more straightforward despite the same initial plan. So then we've got our C2, and these are the coefficients that you'd have for just releasing something if it's critically damped. You don't actually need to know what the mass or the spring constant or the damping constant is to be able to work all of these out. This is a total analytical solution response. Finally, underdamped. This is actually the most interesting one because of these harmonic oscillations, and is the one that's going to be closest to the thing that we had for simple harmonic motion. Nothing in this derivation actually needed b to be non-zero. So the solution we get for underdamped should reduce to the simple harmonic motion one that we're familiar with if b ends up being equal to 0. So in that case, you'd expect that if you release it from a non-equilibrium position at time 0, it would go like a cosine of root k over m, which you might remember from first year, with an amplitude of x0. So after you substitute in the initial conditions, then you find out that we have this form as our general solution. If b is equal to 0, you can verify that yes, it does actually reduce to just x0 times cos of omega d, and omega d was root k over m minus b squared over 4m squared, so that'll be just root k over m. Well, now it's time to explore this differential equation for specific numbers using Maple. So suppose m and k are both 1, and b is 4, 2, and 1, just to make it kind of easy to see what's over critically and underdamped. So this would be critically damped. We can check this. If m and k are both 1, then b squared needs to be 4, so b is 2 if b is positive. Okay, let's get going and solve this with Maple. So with the solution here, we could just copy it in and run that. But let's see if we can build it up ourselves. So we've got the let's hold off on assigning the variables. Let's just put in the differential equation that we got. So the dE would be equal to m times the second derivative of x with respect to time plus b times derivative of x at t with respect to time plus k times x at t. And the differential equation is that this is equal to 0. But like with any solve command with Maple, you don't actually have to say equal 0. You can just put in one side of an equation, and it's going to assume that you mean that that's equal to 0. And the ICs we have are that x at 0 is x naught, and x dot at 0, dx at 0 is 0. Okay, so let's see if we can get this to solve without actually specifying what m, b, and k or x naught are. Dsolve, dE, ICs, let's see. So we do have the solution, just like we found earlier. Notice that it's this form, e to the negative b, and this whole thing that we were getting before. And it has it seems scaled to x naught, which is reasonable given that we're starting at some spot x naught. Okay. Yeah, so we're able to get a general solution, or really a particular solution to this for this exact set of initial conditions. Well, it's a homogeneous differential equation anyway, so I guess I shouldn't call this a particular solution. This is the solution to the IVP, where we've specified the initial conditions here. Yeah, okay, without even needing to know what x naught or m or k are. But if we substitute those in, then we can make this even better. So if m is equal to 1 and k is equal to 1, and let's see, so we'll say x naught is equal to 1 as well. Then we have this, which has different forms depending on b. So without knowing b, we can't do much better than that. But we can substitute a b into this. So let's try subs b is equal to 4 into the differential equation. There. So look at this. We have an exponential term. Now, is it decaying? Well, what's bigger, 2 or root 3? 2 is bigger than root 3 because 2 is root 4, right? So this is decaying down. And this one is even more negative. So these are both decaying exponential terms as expected. Let's go x over damped, and then we can plot x OD for t equals 0 to 5. Ooh. Rookie mistake. So it's not the solution of dsolve. The output of this, which is an equation that you can plot here, you have to plot just the right-hand side of it. So I want to assign not this to all of dsolve. I want to assign it just to the right-hand side of it. So a good way to do this and still look at dsolve is to do something like this. XOD is equal to RHS of mod. Now let's look at the output just temporarily, and so we get just the right-hand side, as you can see there. So let's actually suppress the dsolve output and get this. Okay, great. So next, there's our solution, by the way. In time, maybe to 15, we have a decaying exponential function. So it starts off at 1 and then goes over a little bit, almost. The fact that we've got 2 and they're competing a little bit is what makes it have a bit of a sharper, a more sharply increasing decline at the beginning. Like for the initial second, it kind of has this slow roll off like the start of a coast function because it doesn't realize it's so damped yet. The damping doesn't have any effect until it gets moving anyway. Okay, what's next? Well, now we can try with different b values. So we're supposed to see something interesting when b is equal to 2. And let's call this CD for critically damped. All right. Oh, we have to plot it as well. So let's put that in a list. And what we see for critically damped is that it decays faster. So it looks like it goes down sooner. Let's see what happens. If we take this to 15, the critically damped one goes very close to the origin, no, not the origin, goes very close to the x-axis, very close to 0, quite quickly, and seems indistinguishable from it on this scale after a little bit past 10, but still a decaying exponential function. So critically damped still decays down, doesn't cross the axis. Let's look at underdamped. So we'll take b is equal to 1, for example, and we'll call this x ud maybe, underdamped. Okay, well now, oh, also we didn't mention this, but we've got this as expected decaying exponential and then decaying exponential times t for the critically damped case. And the underdamped case, we have a decaying exponential envelope around a sine and cos function. So we've got this even faster return towards equilibrium. I'm not sure if I want to call it a decay anymore, compared to critically damped. And then it oscillates around. Now the envelope of this last function is larger than the critically damped case would have us return. So we can also kind of figure out what that thing is outside of the sine and cos term. One way to think about this, which matches how you'll deal with it in electronics using phasors, is that here we have one signal, which is 90 degrees out of phase with this one, and this has an amplitude of 1 over root 3, and this has an amplitude of 1. So together, we can make another signal called xud envelope, which has this same e to the negative t over 2 form that these ones have, but then with an amplitude of the root of this squared plus the thing in front of there squared. So that is square root of 1 over root 3, but all squared. So in other words, 1 over 3, and 1 squared, amplitude of this second thing squared. Okay, so that should be the envelope function, and let's plot that as well. Let's see if it works. Okay, so this blue thing now is the just raw decaying exponential, which this cosine and sine term is inside of. So as we continue time forward, the cos and sine term are oscillating back and forth around the equilibrium position, making this thing oscillate back and forth around x equals 0, but with this decaying envelope that goes away like negative t over 2. So that is not as fast as the just negative t decay of the critical damping, and is also, and the negative t decay of the critical damping is also faster than the exponent here. So this is not as large of a number as this one. We've got 1, and we've got negative 2 plus root 3. Root 3 is like 1.7, so this is negative 0.3. Negative 1 is bigger than that. So this is the critical damping is kind of the fastest you can return to equilibrium without actually crossing it like you would in an underdamped case. Okay, so what we have in the notes is the same kind of idea: overdamped, critically damped, and underdamped, and there's slightly different code there if you'd like to go through that for yourself. If you were to look really close, like zoom in around critical damping, then you'd find that the underdamped case is indeed the does always cross the axis, and that's kind of the special thing about critical damping. It will never, it's the one that returns the fastest to the equilibrium position without actually crossing the equilibrium position or ever really hitting it from a math perspective. From a physical sense, it gets as close as you would like to the equilibrium position. So you say it returns there as fast as possible. Now, despite the fact that we set this up with 3 parameters, so like the spring constant, the mass, and the damping constant, you can rewrite the solutions so that they really only involve 2 pretty convenient parameters. And one of these is the natural frequency, root k over m, and the other one is the damping ratio, defined as b over 2 root mk. If you make these definitions, then this damped resonant frequency ends up being omega naught times root of 1 minus zeta squared. That's zeta. That's the symbol. Yeah, so that's kind of neat. And you can rewrite the differential equation in terms of these and the solution in terms of those. And what's nice is then it shows off the fact that there's really just two independent parameters. So by making this definition of damping ratio and this definition of natural frequency, we have a little bit more meaning to these parameters for how they work in a resonant system. Okay, so you'll see those used a lot too. Here is a plot of a bunch of different underdamped systems. You can tell they're underdamped because they're oscillating, and the degree of the underdamping shows how fast they return to equilibrium. So here we have one with almost no damping, and then one with a damping ratio of a 1/16, and then an 1/8, and then a 1/4. So damping ratio of a 1/4, which corresponds to higher B than a damping ratio of an 1/8 or a 1/16, ends up returning to equilibrium and settling down a lot more quickly. Okay, up next, driven resonance and quality factor. Let's suppose that instead of just having this mass spring system that we release or throw with some velocity, we apply a continuous force to it. So we keep applying some force and see what happens. Most interestingly is when we apply a harmonic force. So that is a force that goes like some sinusoid. This is some amplitude, F0, and then sine of omega t. When we put this on, it's going to stay on the right-hand side of this differential equation, because remember we had ma here, and these were a negative bx dot and negative kx on the right side that we brought over to the left. So from a math perspective, this is now an inhomogeneous differential equation. And the way that we solve that is by solving the associated homogeneous one first, which we did up there, and then finding a particular solution to this. A way that you can do that in second year is with the method of undetermined coefficients. And the brief sketch of how that works is you guess that, well, we've got some sine omega t over here, so maybe we can find a solution to this inhomogeneous one if we guess a form of solution that is a linear combination of this function and all of its derivatives. So this only works if there's a finite number of linearly independent derivatives for this function that we happen to be forcing it with, and in this case there are. If you take infinite derivatives of sine of omega t again and again, you'll only ever get two kinds of functions, sine omega t's and cos omega t's, with different multiples in front of them. So this linear combination can represent any derivative of this, and so the method of undetermined coefficients has a hope of working. When we substitute this in to the differential equation, we end up with this sine omega t's, this many sine omega t's, this table kind of helps with it, and this many cos omega t's. If you want to know how this works, to help with the math class, basically what I'm saying here is xp has a sine omega t plus b cos omega t, and then xp prime is negative omega b sine omega t plus omega a cos omega t. And then xp double prime would end up with negative omega squared a sine omega t minus omega squared b cos omega t. So that's how you read the table. I find this a convenient way to come up with the derivatives when you're doing the method of undetermined coefficients, because you can just kind of map out the relationships. So you say, when we do a derivative, then sine will go to cos, and cos will go to negative sine. So to calculate and fill out this table, you just say, all right, we got a, and then the next derivative will have what goes to the cos? Only this, and multiplied by omega. Okay, goes over there. And what goes to the sine? Well, only this one multiplied by negative omega when we take a derivative of cos. So you can sort of see that we go this times positive omega, and then back to another omega over here, but with a negative to give us negative omega squared a and negative omega squared b over there. Anyway, the differential equation itself, the whole left-hand side, is this term sine omega t and this term cos omega t. Then what you do is you compare this to what the forcing function was, which was just f0 sine omega t and 0 cos omega t. So we've got two equations in the two unknowns, a and b, of our guessed solution form. And the equations are that this is equal to f0 and this is equal to 0. So we can solve those. and find what A and B have to be. And if you substitute those in, you have that a particular solution is this. So we solved for A and B using method of undetermined coefficients, and then we can rewrite it as a single cos or sine with a phase constant like this. So the sum of two different cos and sines is equal to a single cos or sine with a phase constant at a different amplitude. This is the amplitude trick I used just in that plot earlier. So A sine alpha t plus B cos alpha t for any A and B, if it's the same alpha, can be rewritten as a single thing there, where R turns out to be equal to root A squared plus B squared, and the phase constant, phi, is the arctan of A over B. To see that, we used that trig thing from the first video, trig primer information, the cos sum angle formula. So cos alpha t plus cos alpha t minus phi is like cos of alpha t plus negative phi. So that'll be cos cos and sine sine. Cos cos minus sine sine for cos, but the sine of negative phi ends up being negative sine phi, so here's the cos difference angle formula derived from that cos sum angle formula and the parity relation for cos and sine. Okay, so what we have there, if you compare left side and right side of this equation, is that the cos alpha t term, for those to be the same, we need that B is R cos phi. And for the sine alpha t term to be the same on left side and right side, we need that A is R sine phi. Okay, so A is R sine phi and B is R cos phi. And then we've got that by squaring these two equations and adding them together, the sine and cos will disappear. So we'll have R squared is A squared plus B squared, and that tells you what R is. Instead, if you divide the first equation by the second equation, R will disappear, and you can see that tan phi is A over B, or phi is arctan of A over B. Okay, so using these relations and considering what we had here, we can rewrite this thing as a different phase, different amplitude, a root of, well, really it's kind of the same amplitude that this sum had. We're just kind of recognizing the amplitude that this thing did have. Okay. This root of this thing squared plus this thing squared, and then a single cosine of omega t with this phase constant. Cool. All right, so this is going to be fantastic for doing some analytical stuff. It turns out that this root is also the same thing we had in the denominator, so we'll cancel out one of them and just end up with this root there. Okay, finally, we're going to rewrite in terms of the natural frequency and the damping ratio, and when we make those substitutions, as before, we can cancel all of the B's and M's and K's, except for, it turns out, one M. One of the M's stays in front, and it's an M that scales the amplitude of the force. And this is kind of expected because mass does matter in terms of the external force that we're applying, but only in that the mass being the resistance to force makes the force scaled inversely with the, or proportional to the mass. This force that you would need to get a certain response would be proportional to the mass of the block. Okay, so then we have this interesting term, this interesting particular solution that, unlike the solution to the homogeneous form, doesn't decay in time, right? Like unlike these solutions we were dealing with up here that we were plotting when we were not forcing it, this does not have an overall exponential decay, right? It's just a cosine, and it has an amplitude which goes like the forcing function divided by the mass, and then is divided by this term here that has some certain interesting special properties. You can see that we're going to be dividing it by more when we have a really large frequency, because the omega squared term will dominate the rest of it. And we're going to be dividing it by less when omega is equal to omega naught, because then this term will cancel out. And that's how resonance works. So in conclusion, the response of this mass spring damper system to a driving force has a new term in the solution, xp, that we would add to our initial, our previous general solution for the homogeneous differential equation, the one without the forcing term, to get the overall general solution to this one with the forcing term. We've got this exponentially decaying thing here that had nothing to do with whether we were forcing it or not. It just had to do with the initial conditions. This is called the transient part of the solution because it goes away after enough time. And then we've got the steady state part of the solution, which is due to this sinusoidal forcing function that we have. Okay. So next, what you can do is check this with Maple by taking this differential equation and then instead putting in the term on the right. So we could modify the previous Maple expression. Let's just get what we need here. So we'll forget we know any of that. We've got this differential equation. We'll say instead equals f naught times sine of omega times t. And we'll forget about the initial conditions and we'll just say dsolve dE. What do we get? Aha, it did it. So we have our decaying exponentials times these constants. See this? Underscore C1 and C2. And then this thing that's not multiplied by an exponential or the constant, which is the particular solution. Okay, let's actually return to this example that we were doing here. So if you've been following along and have the previous one typed in with these different b values, let's modify things and Control J to go down to a new line down here. Let's, instead of specifying different b's at different times, let's fix b to some small number. So b is, let's say 0.5. And now what we're going to do is just solve the differential equation, plot that. Maybe we'll call this just x. Okay. Okay, so first of all, does this work? Yeah, we've got some... this is actually 15 before I hit that other thing. Okay, so here's our block that we've released, and it just goes and stops there. All right, let's imagine instead of this being the differential equation, we'll say x, maybe that's the natural one, that we want to have this thing, dE, instead of being equal to 0, equals some forcing term. So let's imagine 5 newtons times cos of omega. So we'll pick some frequency. Let's say 2 times t. Why not? Okay. Yeah. Now we'll call this thing x forced, and we're going to plot these things together. So what happens if we also force the thing with this function as well? Well, by applying this force, instead of decaying down like this, it goes up and then oscillates back and forth. Now at first, it has this sort of funky response because that's this effect of it starting here, starting not at the equilibrium position, and this transient response that decays away. If we were to wait long enough, then this would look just like this term here. So let's imagine t equals 0 to, how about 80? Yeah. So after a long enough time, the response forgets about this initial noisiness and ends up being just this steady state term. The transient, you can see, has gone away. The effect of the initial conditions is just gone. And we've got just this thing that's left over there. Okay, so here is an effect of this system. This is the solution to a driven mass spring damper system. Okay, now some neat things that can happen. Let's have it start at, well, let's just keep that the same. Let's change around the frequency and see how this looks. See if we can get any interesting effects. Suppose instead of 2, it was 1. What happens? These spread out. Okay. What about instead of 1, it was 5? So we had a much larger response when it was 1 than when it was 5. What's going on there? Well, the term in the denominator here is going to have a modification, is going to modify the amplitude of this thing depending on how big the frequency that we're driving it is compared to things like the natural frequency and how big the damping is. So let's look at some limiting cases. In low frequency, we have omega going very small so that omega naught is much bigger. Okay, so this term here is basically just an omega naught squared, and that's going to be much larger than this term because this is like an omega naught times an omega squared. So forget about this term and forget about this first one. So we have just this thing like an omega naught squared, and then square rooted in the denominator. So that is just like an omega naught squared in the denominator, root k over m. So this just goes like f naught over k. The amplitude is the driving force divided by the spring constant. So this is dominated entirely by the spring. We have at low frequency, the motion is, one way to think about it is if you have extremely low frequency, like no frequency at all, you just apply a force. How far does it move out and stop at? Well, f naught over k, because that's where the spring will balance the force that you're applying. There's no phase shift either. It moves exactly in time with the force that you're applying. So at low frequency, you have that the motion goes like just exactly like the force that you're applying. So let's check that for this different maple example we were doing here. Yeah, so we'll take, let's put in first of all, what is omega naught? Omega naught is square root of k over m. And here, let's drive this at, and I guess we've got our f naught as well. F naught is equal to 5, we're saying. And yeah, so what's omega naught? Omega naught here is 1. Right, of course, because we had mass and the spring constant both equal to 1. So the natural frequency is 1. Okay, so in this, to get the low frequency response, we're going to want to drive this with a frequency that's much less than, or at least, well, yeah, much less than 1. So let's take 0.1. So this moves very slowly, but it goes in phase with the driving force and should have an amplitude which is equal to the driving force f naught divided by k, and totally in phase with the driving force. So let's plot also sine of omega times t. Yeah, let's do this. Let's put in omega there and leave that, and then we'll explore like this. Okay. Ooh, wait, was the driving force sine omega t, or did I use cos? I must have used cos. Yes, of course. In here, where I applied the driving force, I said cos of omega t, so that's what we want to plot to compare it. All right, so we have just f naught over k as predicted, with only a slight shift. So the response of the system in green is almost identical to just f naught over k times the driving force. It's slightly phase shifted back from that. Okay, Let's change things. What about at high frequency? At high frequency, when omega is much greater than omega naught, then we expect the amplitude to go to, so this term is dominant now, f naught over m over omega squared. Unlike this one where we had a constant, this is now the frequency. So as we go to higher and higher frequencies, the omega gets larger and larger, and the amplitude that we're getting gets smaller and smaller. So let's keep the low frequency response on here for comparison, like what it would have responded with if it wasn't for these resonant effects, and increase the frequency. So instead of 1/10 of the resonant frequency, let's go to omega naught times 5 times the resonant frequency. Okay, so this is hard to tell, but the green one here is the much decayed, the much attenuated, I should say. There's this really little green curve there that's attenuated a lot from the response you would have gotten if it wasn't for these resonant effects. So at high frequency, the system can't respond that fast. It just keeps it gives you a much smaller response than you would have gotten without resonance effects. Something interesting happens at resonance though. At resonance, so at omega naught exactly, then this term cancels and you have this term, which depends mostly on the damping. Remember how the low frequency was limited by K? The high frequency depends really on the mass, but the resonant one is most influenced by the damping. So if you have low B, then this term can end up being quite large. Let's check how that one works. So we'll change it to omega naught exactly. And now we need to go to a longer time. Even maybe let's go to 50. Okay, so check this out. We've got a response here. This yellow one is still the same forcing function. This is what we're driving it with. And the green is the system response. So the mass on the spring responds with a larger amplitude than it would have had if there was just if we were just putting this force on it, right? If you just put this 5 Newton force on it for the spring constant of 1, it should only move 5. But even though we have this mass and damper and stuff in it, because we're applying this force at exactly the right time now, the right frequency of this, it can build up energy over time and then steady itself out at this higher amplitude. This thing is limited by the damping. So now, if we were to change B, instead of 0.5, maybe 0.2, we'll find that the amplitude builds up even more before it reaches a steady state. Right, so this amplitude here that we get is limited by the damping ratio, and that's proportional to the damping constant, B. So as we lower B, then we get a higher steady state amplitude. So we have 3 cases: a low frequency response that happens when you drive it with a low frequency forcing function compared to the natural frequency, and then it responds in phase with an amplitude of f naught over k. If you drive it at high frequency, the amplitude goes down further and further with increasing frequency, f naught over m over omega squared, and it ends up being 180 degrees out of phase. Can we explore that? Well, let's have a look here. So we'll go back to the high frequency one, maybe 10 times, and let's plot, instead of f naught over k, let's plot f naught over m over omega squared. Now we should have these kind of on the same scale. Okay, so let's limit our time. We can plot this starting at 40 when it's more or less stabilized. And yeah, okay. So the yellow one is the driving force, and notice that the green one is 180 degrees phase shifted. So it's high when it's positive when the driving one is negative. This is responding totally out of phase. We're driving it at too high of a frequency. System can't keep up, and it is just out of phase with the way that we're driving it. Imagine you're pushing somebody on a swing, but you push them back and forth way too fast compared to how fast the swing can respond. Eventually, they're just totally out of phase. You're pushing the chain back and forth, and they're just swinging totally opposite to you. I can picture that really well. Maybe it's because I have little siblings, but if you push the chain back and forth way too fast, then they'll just be oscillating out of phase with the way that you're pushing them. The most interesting one, though, is the resonant response. So this is what you get if you apply the driving force at the same frequency as the natural frequency of the system. So then we can see that again by getting rid of this times 10 that we had. And now, when we're zoomed in here, it's clear that we have a much larger amplitude than we would have predicted by the high frequency amplitude we're plotting now, but also that the phase shift is 90 degrees. So this is now responding 90 degrees out of phase with the way that we're forcing it. Okay, let's do an example. Plot the position versus time for a mass spring system with omega naught is 10 rads per second and zeta is 1/16th, and we're driving it with a force corresponding to F naught over K is 1 meter. At 3 different frequencies. So let's see, F naught over K is 1 meter. Does that work out? Force, F naught should be units of newtons and K should be newtons per meter. So when we divide F naught by K, we're going to get units of distance, 1 meter. Okay, earlier we went and, well, so now we're given this zeta term, right? You could go and to put this back into M and K things and try and just assume some mass to get it to work, but we don't have enough information to know exactly what the mass is, so hopefully the mass cancels out. We can't figure out mass, spring constant and damping constant if we only know the damping ratio and the natural frequency and F naught over K. It all kind of scales together. So let's first rewrite the differential equation in this form that just used the damping ratio and natural frequency. If we start off with the mx double dot plus bx dot plus kx is equal to F naught sine omega t that we had from Newton's second law, and then divide everything by m, we get the form that had the damping ratio and natural frequency in it over here. But that also points out how this form with no mass in front of the acceleration is going to look on the right. It's going to be this force divided by the mass. So F naught divided by m is what we get on the right-hand side. Problem is, we don't know F naught or m. We do know that F naught over K is equal to 1, and we know omega naught and zeta, so can we rewrite this in terms of things that we do know? Well, yeah. So we want F naught over m, and we know that F naught over K is 1 meter. So that means F naught is going to be equal to K times 1 meter. And we've got a mass down here. Very important to show the italic properly, right? If we weren't putting italic for this mass, it'd be very easy to confuse it with the 1 meter up here in the top. So anyway, K over M is omega naught squared, because omega naught is root K over M. So now we've got omega naught squared times 1 meter. Okay, so there is what F naught over M is, which means the differential equation we're solving is x double dot plus 2 zeta omega naught x dot plus omega naught squared x is equal to omega naught squared sine omega t. So let's fire up Maple here, and we'll put in this differential equation. dE is equal to diff of x at t with respect to t twice, plus 2 times zeta times omega naught times diff of x at t with respect to t, plus omega naught squared times x at t is equal to the thing that we figured out, F naught over m, is omega naught squared times sine of omega t. Let's see. Okay. Acceleration, 2 zeta omega naught velocity, omega naught squared position is omega naught squared times 1 sine of omega t. Okay, so that looks good. We've got the differential equation. We can put in our initial conditions. X at 0 is 0, and the derivative of x at 0, the velocity, is also 0. So this means it starts at the equilibrium position at rest. All right, next we can solve it. I wonder if, Yeah, I think it'll let us solve it even though we haven't put in what the parameters are. Let's see. Oh, system's inconsistent. Maybe not. Maybe it needs to know more about what these parameters are. So let's throw those in. Zeta is 1/16th, and omega naught is equal to 10. How about now? Ah, no good. Well, we'll put in what omega is. Let's try subs omega is 2 into that. Subs omega equals 2 into the differential equation. Oh, maybe I typed something wrong. I wonder if anybody watching sees it. System is inconsistent. Ah, I see it now. The other initial condition I applied was not an initial condition. I should have said d of x evaluated at 0 is 0. Right. Okay, let's go back and see. First of all, this should fix the whole thing. Yeah, okay, we got a solution. What could we have not specified? Could we have left off what zeta and omega were? Yeah, and still gotten something. And what if we didn't even specify what omega was? So we'll just substitute it with itself. Yeah, you can actually do this nonsense subs thing if you don't want to replace it with anything. Okay, so there we go. We can still solve it, even in that situation that we don't know any of these parameters, although we're probably better off putting in some values and now plotting what this is for some different driving frequencies. So before we do this, let's think about the physics that we expect. The natural frequency is 10. So we expect to get the most response when we put in a 10, and the medium response when we put in something below resonance. This is just going to be an amplitude of about 1 probably, and then the least response when we try and drive it at high frequency, because then we're going to be attenuating it. So let's plot, maybe we'll plot all three. So let's say d solve omega is equal to 2, and then we'll go x low frequency is equal to the right-hand side of that. Let's see if that works. Okay, and let's get plotting right away. Plot x low frequency. T is equal to from 0 to, so omega naught is, how can we relate the frequency to the period? So this is something that's, yeah. So if this is the angular frequency, then what it means is that this sort of specifies how fast the sine is oscillating back and forth, but we can relate this to the period, right? If you know what the period is of this function, then you should also know how fast it's oscillating back and forth. So that means there's got to be some relationship where we can uniquely determine the period based on the angular frequency. So let's put in what period means. Period should be the value t, the smallest value of t, such that sine goes through just one cycle before it returns to being equal to this. And that means that adding omega times the period inside the sine has to be the first thing we could have added that brings us back to the previous position of sine. And that means omega t is 2 pi, because 2 pi is the period of sine. All right, so then the period is equal to 2 pi over omega. So if we want an integer number of periods, we should plot an integer number of 2 pi over omegas. Yeah, great. So let's go t is 0 to, how about 10 cycles? That might be kind of a lot. How about 8? 8 times 2 pi over omega. Ooh, omega's changing. Let's just put in the first omega for now. All right, so we should have 8 cycles, right? Yeah, let's check. There's 1. This would be for 2, 3, 4, 5, 6, 7, 8. All right, we did it. 8 cycles. The science is sound. All right. Yeah, so here's our response at low frequency. There's like a little bit of a bump from the initial condition sort of sorting out the transient for this. Let's plot not nearly as many. Let's just go maybe 2 cycles. Sure. Because this is going to get a lot more wiggly when we put in those higher frequency things. Right. Next. Let's go high frequency next. X high frequency would be when we put in omega is 50. That's what they asked us for in this problem. So we can plot that as well. And this should be smaller amplitude than the low frequency response. Yeah, so a lot faster because it's at a higher frequency and much smaller amplitude. Finally, we can put in the resonance. So that would be at 10, and we're going to put in, let's call this X resonant frequency, and let's plot this as well. Okay, so this one, larger amplitude, it rescaled the whole graph, right? The green high frequency one is even smaller. You can barely see it now. The low frequency one looks smaller. It was the whole graph before. And now we have the resonant frequency one, which responds a lot higher because zeta is pretty small. If we were to take, and one thing that's nice about having it all laid out like this is you can pretty easily change zeta down to just like a half or something. And now the resonance doesn't get any higher than the low frequency response. We're still getting the high frequency attenuated a lot because this low damping means it's dropped off quite a lot there. Or rather, this high damping still cuts that down and drops it off quite a lot. Yeah, but we don't have nearly as much of a strong resonance peak as before. Right. So there's some alternate code for plotting this here. If you'd like, you can try and work it out if you'd like a challenge too. So next thing, in this example, determine how the system would respond in response to all 3 excitation forces simultaneously. So here's some interesting stuff. What do you think we would get if instead of, well, let's go back to the zeta that we were supposed to have, 1/16. If instead of applying these 3 forces kind of one at a time and looking at the individual responses, what do you think the response would be if we were to apply them all at once? I'll give you a hint. It has to do with that linearity thing we were talking about. Yeah, so if we imagine that we're going to solve not just this, but this same differential equation equals omega naught times 3 different signs, right? So we're going to have sine of 2t plus sine of 10t plus sine of 50 times t. And now, if I haven't made any mistakes, then we should have, let's call it multiple frequencies, MF. Then we should get the superposition of these 3 responses. Now, because the resonant frequency one is far bigger than the other responses, the low frequency one doesn't end up making much difference to it, and the high frequency one is almost entirely filtered out. So you see something which is basically the resonant response. Now, what if we lower the damping even more? So let's put the damping down to 1/10 of what it was. So zeta is 1/160. It gets a lot closer to just the resonant response. We haven't even reached steady state yet, so maybe we should plot this for more periods at this point. Let's go to 10 of the low frequency periods. Yes, so almost entirely just the resonant response, this blue and yellow curve the same. And if we were to go to 1/100th the damping, here, yeah, there we go, then the thing continues to rise, so we're adding more and more energy. The damping hasn't even shown up yet. If we were to plot this eventually, or long enough, it would eventually kind of level off at some higher amplitude. Let's change the plot time. So let's go from how far did we plot there? We were at 30. Let's go from 40 to 100. It's really choppy right now because we're not seeing, we don't have enough resolution to plot all of the different ups and downs of these functions. You could increase the number of points in Maple if you want to see all of that, by the way. So in case you did want to examine this, you could go, I think num points is equal to 1,000, something like that. And then it'll plot with more points in the plot. That's useful. But usually if you have to do this, you probably should just pick a different range to look at the function in the first place, rather than doing that. So let's go 180 to 200. Yeah, so now we've leveled off. It's not still growing nearly as quickly as it was before. It's more or less leveled off at quite a lot of amplitude. Yeah, let's see. So the steady state amplitude, we said, is supposed to be f0 over k over 2 zeta. And if zeta is equal to 1 over 1600, then 1 over zeta is 1600. So we have 1600 times f0 over k, which is 1. 1600 times 2, or rather 1600 divided by 2, should be equal to 800. So we should end up at an amplitude, once we finally stabilized, of about 800. We don't seem to be there, so maybe we haven't quite stabilized yet. Let's go, t is 1800 to 1805. Aha, so even though it looked like it was more or less steady, because we weren't going over a long enough time range, it was actually still growing, and we do reach up to this 800 amplitude if we wait long enough. You can't even see the original responses now because we have we've amplified this by a factor of 800 compared to the response we would have gotten for 1 if we didn't have resonance. Okay, next let's have a look at this. So plot the log of the steady state amplitude of a natural frequency is 10, that means 10 rad per second, mass spring damper system with zeta is a 16th, to a driving force of f0 over k is 1 meter, or I guess just 1 if we're going to do it in a math sense, versus the log of frequency. So this is plot the log of the steady state amplitude versus the log of frequency, and then repeat for the phase versus the log of frequency. By phase, it means phase shift. Here, the phase shift of the response curve. So these are the things that we worked out. We worked out that the amplitude up earlier, where was this? In this stuff here. When we substituted in limiting cases of driving frequency, low frequency response, we said limits to this and no phase shift. High frequency response limits to this amplitude and that phase shift, and resonant response limits to this amplitude and a pi by 2 phase shift. But how we got this is by looking at limits of this and this. So these things that we derived even earlier than that were the formulas for the amplitude and phase shift. So what this question is asking us to do is to substitute in known values for f0 over k and omega naught, and then plot this whole thing versus omega, versus the driving frequency. So we're going to substitute those things in, make the plots, and the code for doing this with Maple is in the plots package. You have to include plots, and then you can make a log plot, new command, of the amplitude that we typed in just from that earlier function. From omega is 1 to 100, and then a semi-log plot. This is linear versus log of the phase shift, and now we've converted it to degrees by multiplying by 180 over pi, from 1 to 100 as well. So we're just plotting for a frequency of 1 to 100. This is a weird way that this version of Maple reports that 0.1 E3. In other words, 1 E2, right? So 100 is 0.1 E3. Okay, so the amplitude does what we expect. If the low frequency is 1, then it is pretty much constant with increasing frequency because the omega term doesn't matter compared to the term based on omega squared. And then rises up at resonance to when this term perfectly cancels with the what was that? The omega naught squared term. This is part of the combination of those two, so it's a little hard to see which term exactly is which here. This subtraction would come from a combination of the cross term from these two, and then this thing here, which is based on omega naught and omega. So it's hard to say which is exactly which. But anyway, when you combine them, you have a minimum in the denominator at resonance, and that is where we've risen up to this higher amplitude, and then we start dropping off like 1 over omega squared, which looks like a straight line on a log-log plot. We also see the phase shift stuff that we calculated before, where it's 0 phase shift at low frequency, then 90-degree phase shift at resonance, and a 180-degree phase shift at higher frequencies. Usually, this is all discussed in the language of quality factor. The quality factor of a resonator is the amplitude at resonance, this height, divided by the amplitude you would have gotten at low frequency, which in this case is 1. So this tells you about the system, not about the driving force, right? It's a property that should depend just on the mass and spring itself, not and damper, that mass spring damper system, not on the nature of how you're driving it. So if you know this quality factor, then you can determine what the response will be at resonance if you know the low frequency response. So if we take the amplitudes that we calculated for those limits, at resonance we have f naught over k over 2 zeta, and at low frequency it was just f naught over k, so this ends up being 1 over 2 zeta. Right. Yeah, you might remember that this is a thing that we just found out in that maple example that we did. So when we looked at really high frequency, or not really high frequency, 1805, we wait a long time and we look at what the amplitude is. So the amplitude at resonance is 8. So what's zeta? It's a 16th. So 1 over 2 zeta is 8. And because the low frequency response, f naught over k, was equal to 1 this time, then we end up with 8 times that. If we were to change f naught, let's imagine we multiply f naught by 1.5. So we change our differential equation to be not equal to this thing, but instead be equal to 1.5 times that. What should this do to the yellow curve? We haven't modified the blue curve here because that was typed in this equation here later. But what it should do to the yellow curve is increase the amplitude by 50%. So it should go up to 12. Yeah, 12. So there's 10, 11, 12. Yeah. So the quality factor of this system does not depend on the driving force. It's the same quality factor regardless of what force we're driving it with and what frequency we're at. This tells you about how the thing behaves around the resonance. If you were to actually drive it at the resonant frequency with a signal like this, when omega is 10, then the quality factor being 8 for this system tells you that at resonance, you'll get 8 times the response that you would have gotten if you drove it at low frequency. So this quality factor tells us about how it is one way to characterize why the response is so much higher here. If we reduce the damping by a factor of 100, the quality factor goes up by a factor of 100. So now we have a quality factor 800, and that is and that tells you that the response is going to be 800 times what you would have gotten at low frequencies. Quality factors can be quite large, right? So in resonant systems, you'll see papers with quality factors in the billions and even hundreds of billions for optical systems that allow you to have really amazing responses in certain physical situations. So why you want a large quality factor is to do with this filtering effect. First of all, you can get way more response and clean signals with being essentially just the resonant effect, even if you weren't driving it with only the resonant effect. And this is one way that that lasers can have such a specific frequency that's coming out of them, and also that your computer can keep time so precisely is by leveraging these resonance effects one way or another. So this is one definition of quality factor, the amplitude at resonance over the amplitude at low frequency. But it turns out there's some other definitions which end up being equivalent. You can also define quality factor as 2 pi times the peak energy stored, the maximum energy that's stored in this resonator system, divided by the energy dissipated per cycle. Can we prove that? Well, the maximum energy stored for this mass spring system would be half kx at the maximum displacement. And if we're at resonance, then it's F0 over k, which is the low frequency 1 over 2 zeta, all squared. So here's the peak energy stored. The energy dissipated per cycle is a little bit more tricky, right? So we'll say the energy dissipated per cycle, you would have to integrate over the cycle the force dotted with the displacement. But the damping force is, so this is, let's see, energy, why is this a negative? Because we're talking about energy dissipated. So the work done by the damping force would just be F damping dot with this displacement. But we want the work done on the damping force, the dissipated energy, and that's where the negative comes from. Now, because the damping force itself is negative, this ends up creating another negative inside. We factored the first one out to give us a positive thing overall. The damping force is dissipating energy. Okay, so we end up having the average over one cycle, integral over the full cycle from one period of the velocity will give us the average, would give us 0, but this is integral of velocity squared because we had 2 velocity terms. Where did those come from? Well, we have one from the damping force itself, the fact that it's proportional to velocity. And we have another one to put this in terms of time. The little bit of displacement is dx by dt times dt. So we end up with a velocity squared term inside, and this is what leads to a net energy dissipated rather than just kind of storing energy and giving it back. These being in phase lead to a non-zero average energy dissipated, unlike the work that would be going into the spring force or the mass, which are 90 degrees out of phase with the velocity at resonance one way or another. The work that's going into the damping is lost. We don't get that back. So there's some math that works this out in detail. Essentially how it works is the velocity is this expression. So we end up with a bunch of constants that we can pull out, and then the average of a cosine over average of a cos squared over a cycle. And the average of a cos squared is a half, because a cos squared plus a sine squared would be 1, and these are just as big on a cycle on average. So the average of cos squared by itself must be just a half. Okay, so we've got a half times this stuff times b, and that is this, integrated over one cycle with respect to time, so that gives us one period there. All right, because the period is related to the frequency, we could simplify this more right now by subbing in 2 pi over omega, but let's just jump right to what we really want to calculate, which is 2 pi E max over E dissipated per cycle. Subbing in what we calculated here for the maximum stored energy and the maximum and the total dissipated energy per cycle that we just found, we have this expression. Okay, let's clean it up. The half cancels with that half. We've got the 2 pi sticking around. There's a k, and there's a divided by k squared and an f0 squared that cancel. The zeta cancels. We're left with an omega naught squared. The b is still sticking around. The t turns into 2 pi over omega. And then we can cancel one of those omegas. We can cancel the 2 pi. We're left with a k over b and the 1 omega left. That's it. Okay, so then omega becomes root k over m, and we can rewrite this a little bit more, root mk over b, but hey, that is 1 over 2 zeta. if we go back to where we defined the damping ratio earlier, zeta was defined as b over 2 root mk. So root mk over b would be 1 over 2 zeta. Aha. And that demonstrates that this 1 over 2 zeta, which was the quality factor by the first definition, is the same as this much less obvious thing that would also happen to be the quality factor of 2 pi times the energy stored over the energy dissipated per cycle. Okay, so there's one more definition of quality factor, and this one is going to require quite a complicated proof. But prior to diving into that, what I'd like to do is just kind of see what it means. Like, let's use it and just get kind of a feel for why this might be true or what it's even saying. So this says that the quality factor is the resonant frequency, the natural resonant frequency, divided by the full width at half maximum of the power response curve, relative power response curve. So what is the relative power response curve? To get a feel for this, let's jump down to the code for this, which is kind of useful for plotting some of these things. So this one has grid lines in it, and we're going to want that to be able to read things off the plot. Okay, so I'm going to copy this code into Maple and get rid of these symbols that we don't need. Okay, yeah, so here are a bunch of different power response curves, or really amplitudes. This is just amplitude versus frequency. Yeah, so the top one here is zeta is equal to a 16th, and then we've got zeta is an 1/8, and zeta, the damping ratio, that is, a quarter, a half, and then 1 and 2. So we could also write out what quality factors these correspond to. Let's see. So the quality factor is 1 over 2 zeta. So Q1 is 1 over 2 times 1 over 16, right? So the top one is a quality factor of 8, and then we're going down in factors of 2. So this thing here has a quality factor of 8. Now what we are asserting is that by this third definition of quality factor up here, is that the quality factor should be equal to the width of not the amplitude versus frequency, but the power versus frequency at half of the maximum. So first we're going to need the power versus frequency. And that means we are going to plot the square of this thing. So rather than amplitude, let's get another plot here. Let's plot kind of a, I wonder how to do this conveniently. Maybe we'll just say that we want to plot, okay, let's save that thing, and we'll call this one, maybe we'll do P at a 16th, at an 1/8, P at a quarter, P at a half, P at 1, and P at 2. And how are we going to get P? Well, we're going to say that P is a function that takes zeta and subs it into A at zeta squared. Okay, that should work. And now we should have relative power. Okay, actually, this would be just kind of regular power. So since this goes to an amplitude of 2 at this point, if we want power to be power relative, then we're going to want to take this and divide it by the same thing when we substitute omega is equal to 0. So let's take this divided by subs W equals 0 into A at zeta. Yeah, I think that should work. Okay, so the relative power should be going to 1 at this left end. So let's just check. If we take omega is 0.1 to some small number, 1, does this go to 1? No, it doesn't. How come? Oh, what we're plotting is 2 times this thing. So for some reason we were plotting 2 times this up there, and the amplitude was only taking us to the number 1 at the origin anyway. So okay, I guess that's kind of working. So this one should now take it to a 1. But also, even if we now make our amplitude not have a base offset of 1, but like 5 or something, then this relative power spectrum should be the same. So now the amplitude graph, let's plot that too. The amplitude graph goes over to 5, but the relative power spectrum is normalized so that it still scales to 1 at the left, because what we're plotting is the power compared to the power that you would have at low frequency. Now power goes like amplitude squared. This is true for a mass on a spring, but it's also true for other systems that we're modeling with resonance. With this same setup, remember that this linear system resonance is applicable to a lot of physical systems, not just masses on springs, but for masses on springs, for example, the power is proportional to the energy, right? And the energy goes with velocity squared or with displacement squared. So the amplitude is going to be proportional to the power after you square the amplitude. So amplitude itself, I shouldn't say, is proportional to power. Amplitude squared is proportional to power. And that's why we square this here. So we take the relative power compared to low frequency by taking the amplitude at some point compared to the amplitude at low frequency and squaring it. That's how you get this thing. Okay, so yeah, still with me? This is a monster definition to understand. Okay, now that we've got this plot here of relative power, we'll put back the larger range. Let's take it to, how about 20? That seems good for seeing this curve. What we would need is the full width of this thing at half of the maximum value. So the maximum for the red curve here looks like it's about 65. So the half max would be 65 over 2. This line. Now, this doesn't line up very well with our grid lines, so maybe I'll cut the plot down a bit. Instead of going 0 to 20, let's go 5 to 15. That should make it line up a little bit better. Okay, not quite easy to read off of this thing. Let's spread it out a bit more. I guess the business stuff is between 9 and a little after 9 and around 11 there, like 10.5. So let's plot from that range. From 9 to 11, it looks like now we're seeing this intersection at 9.3 and this other intersection at about 10 point, closer to 10.6. Okay, so then the full width, d omega, would be equal to, full width at half of the maximum in the relative power spectrum would be at about 10.6 minus 9.3, I think. Yeah, that looks right. Okay, so that should be d omega, and then we'll take omega naught, the resonance, which is about 10, and divide that by this. And that means that the quality factor for this system should be about 7.7 by this measurement. So this full width at the half max in the power spectrum, it was a bit tough to read it off the graph, is giving us about 7.7. And this is kind of a neat graphical technique. Once you've got a power spectrum, which you could get by measuring the system's response and sweeping the frequency, then you would have a plot like this. You could, off the graph, do some measurements of what the width was at the half max and come up with a really quick, fast calculation of what the quality factor is if you know nothing else about the system. So this is a really experimental based measurement. And it also helps you talk about what the quality factor means, right? So the quality factor being the full width at half maximum tells you about the the frequency divided by the half width, the full width at half maximum, tells you about the sharpness of the peak. So at a given frequency, if you divide that by this width, then a high quality factor will have a really high, being like a sharp peak here, tells you that it's going to have a really thin kind of half width, right? So this also helps characterize what we're talking about when we talk about quality factor, like helps understand what it even means. Okay, so this reading off the graph technique was kind of rough, but we can be a little bit more numeric with it using Maple. So we can find out what the real max value is, not quite 65, by just using valve of maximize p at a 16th. And it turns out it's close, it's 64.25. So then the other thing we can do is see where the function is equal to half of this max value by using fsolve on this range, W5 to 10. Find out exactly where this intersect is. And it says it's 9.3. And the one on this next range, between 10 and 15, we can use the same fsolve and find out 10.56. So now let's see what we get. Q V3, like the V3 of how to calculate Q, should be equal to max val divided by, hope I do this correctly, it should be this one, which is the previous result, minus 2 results ago, this thing. Okay. Yeah. So that doesn't seem right. Oh, yeah, of course. It's not the max val divided by that. It's the resonant frequency. And that, I think we had a variable for. Yeah, W0, exactly 10. Okay. So, very close. Not exactly 8, but a lot closer to 8 than we were getting from here. And still kind of justifying because we're in the right range, the reading off the graph does imply that we're not way off with this calculation. So, as you can probably tell from that, this is going to involve an approximation. Let's see how it works. Well, the frequency-dependent steady-state response is this again. And if we want to write what the amplitude is compared to the DC amplitude, then we would divide this by the DC amplitude, the low-frequency amplitude, I mean by that. This is a circuits term, so if you hear me say the DC thing, it probably means low frequency. Okay, so low frequency response is this. We take this divided by f0 over k, and we get k over m in the numerator, which is the same as omega naught squared. So we could simplify this, especially after we square it to get the relative power response. By dividing by omega naught squared and simplifying it up a bit, you can see that this whole thing is really just in terms of two distinct variables. So we'll rewrite them. Omega and omega naught always show up together, so let's just call that omega over omega naught thing, omega r, the relative frequency. And then just for even more convenience, instead of dealing with 4 zeta squared, we're just going to call that xi. Give it another Greek symbol, why not? Okay, so the omega frequency relative to the natural frequency, this is a variable. It's just kind of scaling and forming dimensionless frequency, really. And this one is already dimensionless. It's just a more convenient dimensionless thing that shows up in this. All right, so next, what we're going to do is say that if we were to substitute in the frequency where we are at the half width, the frequency where this is half of the resonant response, then we should get half of what we would have gotten at resonance for this power, right? And what do we get at resonance? Well, at the resonant response, when we put in omega is equal to omega naught, then this is just a 1. And this one's a 1, so that cancels. So you can see the resonant response is 1 over xi. So 1 over 2xi is what we would get when we're at these half widths. And we expect to find two of them, one on the left side of this resonant spot and one on the right side of it. So, not surprisingly then, we do end up with a quadratic here in omega r squared. After simplifying it out, we can find that omega r squared must be equal to this thing. And next, we say, assuming the damping is small, then zeta is small, and xi being 2 zeta squared is probably going to be really small. So maybe 2 minus xi is basically 2, and this root of xi squared plus 4xi is basically root of 4xi. We don't need this xi squared thing there. So that means we can get that this is essentially 2 plus or minus just root of 4xi, and then letting the 4 come out and cancel and become a 2, and then all the 2's cancel. We're left with 1 plus or minus root xi, which is 1 plus or minus 2 zeta, considering what xi was. Okay, so then the omega r's are 1 plus or minus 2 zeta. And we need the positive roots of this. So even though we were okay with taking the negative root for 1 plus or minus root xi, we need the relative frequency to be positive. So that means we're left with the omega r is the root of 1 plus, positive root of 1 plus 2 zeta, and root of 1 minus 2 zeta. And the width would be the difference between those two. So remember that omega r relates to the frequency we're actually looking for by multiplying by omega naught. So after we put that through, we can finally see that the half width is omega naught, omega r positive minus omega r negative, and that ends up being this. Next, we're going to use just one more approximation, which is a binomial series approximation, which in the instance that we need, 1 plus something all to the power of a half is basically, as long as that something is small, like xi is, 1 plus a half that something, plus other things that go like that something squared. And we're going to say that the 2 zeta, when squared, is small compared to just 2 zeta. So forget about these higher order terms, and then, but we need the first zeta term because the 1's are going to cancel. So we're left with delta omega is omega naught times 2 zeta. All right, so then finally, we've got that omega naught over delta omega is 1 over 2 zeta, which is the quality factor. Drop the mic. We did it. Here's the proof of this complicated definition of quality factor, and that shows that as long as the damping is low enough that you can make these assumptions, then the 3 definitions of quality factor are the same. To recap, we have 3 definitions of quality factor. We have that it's the amplitude, amplification, and resonance, that it's 2 pi times the ratio of peak energy stored to energy dissipated per cycle, and that it is the resonant frequency over the half width in the power spectrum. And this third one only works if the damping is small enough that you can make approximations along the way that we made here. So we made one approximation that 2 minus this thing is basically 2, and that this thing squared compared to 4 times itself is basically 0, and that we don't care about order of zeta squared terms when writing out this series. Okay, so we're left, well, really, actually, I guess the order squared terms would have canceled because they would both have been the same sign. So we actually just neglected the order cubed terms compared to the first order terms in zeta. Okay, so with all of those assumptions, this third one will only work if damping is small, and if that's true, it means that this calculation that we had should get better if we had a lower zeta, right? If we had a lower damping ratio, then maybe we're going to get closer to the actual Q. So let's put in actually what zeta is. So if zeta is 1/16th, then we've got Q is equal to 1/2 times zeta, right? And we can put in zeta here. So we'll put zeta there, and zeta there. Okay, so then if Q is 8, using this calculation, we find that this Q is 7.96. And maybe we'll take we can form the relative error by taking QV3 minus Q over Q. Okay, so we've got negative 0.4% as our relative error in using this frequency over the half width and the power spectrum definition for Q. What if we take zeta to be smaller, so 1/32 instead? It gets to less error, right? It's now about 0.1% error. What if we take it even smaller? What if we're talking like 1/100? Now it's 0.01, 1/1000. Not 0.01, but 0.00. Hold on, am I doing this right? Yeah, 0.0001. Wow. Okay, so this gets very small as we go closer. It's not scaling down proportional to just kind of quadratic in this either. These approximations get better and better as zeta gets smaller because, you know, we were neglecting cube terms and quartile terms with this. So these if zeta is small, you have a high quality factor resonator, like a quality factor of 5,000, the relative error in using something like this is 0. Even if your quality factor is only 50, then the relative error is less than 0.01%. But if your quality factor is is only 2, then you've got a 7.5% error there. And you see this didn't even work when we put in zeta as a half. What's going on there? Well, up here, you can see what's happening for the zeta is a half curve. Well, maybe you can't because it's so small of a peak on this. So let's change the other label here. Maybe, so W is this. So actually the amplitude one shows it better. The zeta is a half term, which is this blue one, does not have a peak frequency at the same spot anymore. The curve is moved so much that there actually isn't a location to the right of 10. We previously said look from 10 to 15 for the spot where it's equal to the half max, where the curve is equal to half of the increase from low frequency. You can see that on the power spectrum by changing the axis. I think we go P equals let's say 0 to 2. Right. So here to the right of 10, there's no spot where we have half of the power amplification that we had at resonance anymore. In fact, the idea of amplification kind of falls apart when we're looking at this graph here, because what does half of the amplification mean? We really said half of the peak, right? But the peak is so small that to take half of it gets us below the starting point. And that's why we couldn't find it. It actually was the left intercept with half of this that we couldn't find, because it just goes to 1 on this. And we were telling it to look for where it goes down to half of this peak. But the peak is so small that there isn't this point anymore. So the low quality factor curves, the ones with high zeta, high damping, are have such small peaks, if they even have a peak, that this approximation doesn't even it's not even clear how you would interpret it to say that you have a resonant frequency peak, and then you look for where you have half of that amplitude on each side, half of that peak height on each side in the power spectrum. Well, half of this on the left side, you never get there, right? So this is a fine definition. If you have a high quality factor, at least something like 4 or 8, but when you have a quality factor of 1, this is not a very good definition. You can also see the other things sort of fall apart too. So this zeta of a half, 1 over 2 zeta should give us a quality factor of 1. And this is telling us that the amplitude amplification at resonance should be 1. And yeah, sure enough, it is 1 here. It's the same size here as it is over here. But the problem is this is not even the peak anymore, right? The peak is shifted to the left compared to where the natural resonant frequency is. So this is the effect that damping has on let's say resonant frequency, on peak frequency. When you have high damping, then the highest response is technically a little bit to the left of resonance, or a lot to the left if we have overdamped systems. Okay, so there's a couple more examples here. The first one just has you substitute in the definition of Q to replace the zetas, because since Q is 1 over 2 zeta, you could also write the total response in terms of the quality factor instead if you wanted. So this is the total response function that we worked out earlier for this linear system. And now instead of zeta, we've got quality factor. So you can see how that plays in. Higher quality factor will mean a lower damping amount here, and that's going to mean a higher resonant peak. You also can figure out, in terms of quality factor, how many cycles does it take for the transient response amplitude to drop to 1 over E of its initial value. And that's something you can determine by looking at this envelope here. So the transient term, this thing in front, has an exponential decay of e to the negative omega naught over 2q times time. So this will be multiplying it by 1 over e when this exponent is -1. So that's when omega t over 2q is 1, which means you need a time of 2q over omega. And substituting in the omega as 2 pi over t that we found out earlier, that's q over pi periods. So that's how long it will take for the amplitude to drop to 1 over e of its initial value. How long would it take for the power to drop to 1 over e of its initial value? Well, the amplitude would have to drop to only 1 over root 2 of its starting point for the power to drop by a factor of 2, because power goes like the square of amplitude. So that means instead of setting this equal to -1, we would set this equal to -1/2, which would cancel the 2 that canceled earlier. So we would have t is equal to qt over 2 pi, half of this time, to drop to half power. So that brings us to the end of the lecture. A grand summary here. A mass on a spring with a constant k subject to linear damping has a differential equation of this. If we're also driving it, it gets modified by this on the right. And there's 3 distinct regimes. Overdamping is when b squared is greater than 4mk, which just means it's going to return slowly to equilibrium. If instead we have critical damping, it's going to return as fast as possible to equilibrium without ever crossing it. And if we have underdamping, b squared is less than 4mk, then it's going to harmonically oscillate at its natural resonant frequency, but with an amplitude that decays exponentially in time. This doesn't mean like really fast necessarily. It means it decays according to an exponential function. The decay can be very slow if the damping is low. If you have a driving force that has a frequency at or close to the resonant frequency, natural frequency of this system, then it's going to have an amplitude which is larger than you would have had if that same force was applied at a lower frequency or a higher frequency. Other common terms you'll see around this are the natural frequency, omega naught, root k over m, the damping ratio, which is this zeta, b over 2 root mk, and quality factor that has a number of different definitions, the amplitude amplification at resonance, 2 pi times the max energy over the energy dissipated per cycle, and as long as Q is large, which means, well, depending on how accurate you want to be, could mean something like 4, but better if Q is something like 50, then Q is also the resonant frequency over the half width in the power spectrum. For a linear mass spring system, Q is equal to root mk over b. So it's not this for other systems because there isn't really a mass or a spring constant if you're talking about something like an RLC circuit, but it is still this with the equivalence of mass, spring constant, and damping constant. Okay, typically solving a DE for this with computer power would mean just typing out the differential equation coefficients and the differential equation and the initial conditions and then solving it and plotting it. But all of this analytical work that we've done over the last 2 hours is really helpful for understanding what you should be looking for and the effects we're looking for. So hearing it and seeing these things are only the start, though. You've got to try some examples yourself to get a feel for how this works, in particular with some of the examples corresponding to double resonators. And those are going to be the subject of the next video. Thanks for watching. I'll see you then.